August 20th, 1942, early morning. Lake Patricia in the Canadian wilderness. The surface of the water is still, cold air hangs over the forest. You can almost feel the isolation. Only a few wooden huts stand near the shoreline. Inside these huts, a small team of British and Canadian personnel prepare equipment for an experiment that few outside Allied intelligence even know exists. At first glance, nothing here suggests the creation of a revolutionary weapon. Yet hidden in this quiet landscape is the beginning of Project Habakkuk, a plan so unusual that even seasoned military leaders struggle to accept it. A plan to build an enormous aircraft carrier from frozen water mixed with wood pulp. The idea originates from Geoffrey Pike. Pike is an advisor within the Combined Operations Headquarters under Lord Louis Mountbatten. He searches constantly for unconventional solutions. He studies material science. He explores engineering puzzles. His ideas often seem impossible, yet some become reality. During the height of the Battle of the Atlantic, German U-boats strike Allied convoys with devastating effect. Supply ships vanish beneath the waves. Aircraft patrols lack sufficient range to protect distant sea lanes. The gap between land-based airfields creates deadly zones where German submarines hunt freely. The need for a new strategy grows urgent. Pike presents an audacious concept: build a floating runway from a new material that is stronger than ice alone. The substance is called pykrete. It is made from frozen water mixed with wood pulp. When frozen, it is remarkably tough. It resists shattering. It melts slowly. Tests show that a block of pykrete can withstand bullets that would pulverize normal ice. The concept is simple in theory. Construct a giant barge or carrier made from this reinforced ice. Keep it frozen with refrigeration units powered by onboard engines. Tow it into the mid-Atlantic. Use it as a base for long-range aircraft. With this platform, Allied planes can patrol areas previously unreachable. German U-boats would lose their advantage. Lake Patricia becomes the testing site. Engineers build a small-scale prototype from pykrete. The structure rises above the dark water like a strange frozen monument. It must endure seasonal heat. It must resist cracking. It must prove that the material can be shaped and maintained on a large scale. Inside the huts, men work with saws and pumps. They cut blocks of pykrete. They measure temperature loss. They test strength with controlled impacts. The ice composite surprises even experienced engineers. It bends rather than shatters. It holds weight far beyond expectations. Yet the challenge remains enormous. A full-size vessel would be one of the largest structures ever attempted. It would require thousands of tons of pykrete. It would need refrigeration throughout its hull to maintain shape during long voyages. It would need protection against torpedoes, artillery, and ocean storms. Still, the idea advances. The British Admiralty reviews early results. Lord Mountbatten himself presents the concept to Winston Churchill during a meeting. Churchill is intrigued. He gives permission to continue. The project moves from experiment to potential wartime solution. Back at Lake Patricia, the prototype endures the first signs of warmer weather. The team monitors every crack and shift. They make notes. They adjust calculations. The men understand that success here will determine the future of Habakkuk. But uncertainty lingers. Can pykrete remain stable under the harsh conditions of the North Atlantic? Can engineers design a hull large enough to carry heavy bombers, while also keeping the structure frozen from within? And can wartime industry spare the machine's manpower and energy needed for a floating fortress? The next phase will reveal whether the bold idea survives beyond this remote lake. Autumn 1942. The forests around Lake Patricia grow colder again. Wind moves across the water and rattles the thin ice near the shore. The small pykrete structure still floats. It survives heat. It survives rain. It survives repeated stress tests. News of these results travels quickly through Combined Operations Headquarters in London. Technical officers gather around diagrams. They examine tensile strength charts. They study refrigeration models. Project Habakkuk is no longer a curiosity. It becomes a potential strategic asset. The core idea remains simple: a vessel longer than a modern battleship, a hull made from pykrete that resists impact, a giant internal cooling system that keeps the ship frozen, a deck wide enough for heavy bombers, a platform that could stay at sea for many months. Yet the engineering challenge grows with every calculation. The proposed carrier would require an internal skeleton for stability. Steel would reinforce critical areas. Wood pulp and water would fill giant molds. The entire hull would be a frozen composite. Engineers sketch cross-sections. They calculate heat loss. They design networks of refrigeration pipes. They plan internal compartments for generators and compressors. They test structural loads using scaled models. Canadian scientists join the effort. They evaluate the local supply of wood pulp. They estimate production capacity. They review transport possibilities. The sheer amount of material required is staggering. To build a vessel of the proposed size would demand timber from vast forests. It would demand freezing plants running night and day. It would demand labor on a scale rarely seen in wartime construction. Some engineers raise practical concerns. Pykrete is strong yet sensitive to temperature shifts. In warm seas, the hull would require constant cooling. In storm conditions, the outer layers might crack. Allied ships must navigate rough waters. An aircraft carrier made from frozen composite must endure waves that rise like moving cliffs. Meetings in London grow intense. Admiralty officers study new reports daily. Some support the project willingly. They argue that the Atlantic Gap is a deadly threat. They believe a floating airfield could change the course of the naval war. Others remain skeptical. They question whether Allied industry can support such an enormous undertaking. They worry about diverting steel and engines from existing warships. They examine potential vulnerability. Torpedoes might not sink a pykrete hull easily, yet fires, or repeated hits could damage refrigeration units. Once cooling fails, the entire structure begins to weaken. During this period, the prototype in Canada continues to serve as a laboratory. Workers drill holes into the pykrete block and insert thermometers. They record data for every hour. They test melting rates. They study stress under controlled weight loads. The small structure remains intact well into the cold season, proving pykrete has genuine durability. Geoffrey Pike continues to promote the concept through constant reports. He highlights scientific studies. He emphasizes that pykrete is lighter than steel at full volume, yet can be shaped in massive sections. He notes that even if construction is slow, the vessel would offer a sustained presence in the Atlantic. Aircraft could take off and land without the limitations of fuel range. Convoys could receive cover across the entire ocean. New design proposals emerge. Some show a vast rectangular hull. Others present rounded shapes to improve stability. A few include defensive gun positions. All plans rely on an internal steel frame. All require powerful refrigeration plants to keep the structure frozen from within. By winter 1942 into early 1943, the project reaches a critical stage. Technical teams in Britain and Canada prepare detailed assessments for the highest levels of Allied leadership. They calculate cost in materials and manpower. They evaluate shipyard capacity. They examine energy demands for refrigeration. They compare these needs to existing wartime priorities. The results are mixed. The concept is scientifically possible. Pykrete works. The structure can hold shape. The idea could transform Atlantic warfare. Yet the required scale borders on unimaginable. Entire factories would need to shift production. Steel for the internal frame might reduce output of conventional warships. Refrigeration units would demand fuel that is already scarce across the Allied world. At the same time, German U-boats continue to strike at sea. Convoys face danger in regions far from air cover. Mountbatten urges continued study. Churchill remains intrigued. Allied commanders ask for more tests. Lake Patricia now becomes a symbol of ambition. A quiet place where a small prototype floats, while generals and scientists debate the future of naval warfare. A place where an idea born from desperate necessity might shape the outcome of the Atlantic struggle. The pressure grows. A final decision approaches. The next phase will determine whether Project Habakkuk becomes a full construction project or remains an experimental dream frozen in the northern Canadian wilderness. What factors will decide its fate as the war enters a new year? Early 1943 arrives with tension across every Allied command. Technical teams finalize their reports. They deliver binders filled with calculations. They outline strengths. They outline weaknesses. They outline the vast demands the project will require. Two questions become central. Could the Allies build it? And should they build it? Meetings begin inside the highest levels of wartime planning. Strategists compare the potential impact of a frozen aircraft carrier to the immediate needs of the Atlantic convoys. They study shipping losses. They study the pace of U-boat attacks. They study the limited number of escort carriers currently available. The arguments grow sharper. Supporters present a clear vision. A giant stable airfield in the ocean would allow long-range patrols. It would deny German submarines the freedom of the mid-ocean gap. It would save merchant ships and lives. Skeptics counter with hard numbers. They list the wood pulp required. They list the refrigeration equipment needed. They list the steel that must be diverted from frigates and destroyers. They question the timeline. They ask whether a vessel hundreds of meters long can be frozen fast enough to meet wartime needs. Cost also becomes unavoidable. Refrigeration plants would consume fuel around the clock. Labor demands would stretch Canadian facilities to capacity. Energy grids would require new expansion. Every day of delay means more convoys under threat. Churchill receives the latest assessments. He reads them with interest. He circles notes in the margins. He asks for clarifications and new estimates. Mountbatten continues to champion the project. He argues that no other concept offers such reach across the open ocean. He insists that bold innovation is needed to shift the balance of the naval war. American officials also review the data. Some see promise. Others worry that joint resource commitments may slow existing shipbuilding programs. The United States is already constructing escort carriers in growing numbers. They question whether a frozen supercarrier is still essential. Scientists add their voices. They confirm that pykrete can withstand impacts that would shatter normal ice. They confirm that it melts slowly if cooled from within. They confirm that the structure can be shaped in enormous sections. But they also warn about temperature. Warm waters in the South Atlantic or Pacific could challenge the refrigeration system. Engineers must design cooling lines running through every part of the hull. A single failure could weaken the vessel during operations. As these debates intensify, the prototype in Lake Patricia remains steady, frozen, unaffected by wind or weight, a silent witness to global decisions taking shape far away. The next step requires commitment. Construction on a scale never attempted. Industry redirected. Shipyards rearranged. Engineers deployed across remote northern regions. Generals and admirals prepare to deliver their final recommendation. The fate of Project Habakkuk now rests on strategic necessity, material cost, and the unpredictable course of the war. A decision must come soon, and once made it will shape the future of the Atlantic. Spring 1943 arrives with a shift in the Atlantic War. New escort carriers enter service. Improved radar reaches convoy routes. Long-range patrol aircraft fly farther than before. U-boat losses rise sharply. German commanders face mounting pressure. The mid-ocean gap begins to close. These developments alter every calculation surrounding Project Habakkuk. The urgency that once drove the concept now softens. Allied leaders review updated reports. They examine new convoy survival rates. They compare recent shipping data to the dark months of 1942. They see progress. They see fewer losses. They see the growing strength of conventional solutions. The giant frozen aircraft carrier no longer appears as essential as before. Technical officers highlight the remaining obstacles. Refrigeration demands remain enormous. Material requirements remain vast. Construction time remains long. Shipyards already strain under the load of destroyers, frigates and troop transports. Energy grids cannot easily support the cooling plants required. Fuel shortages complicate every stage of planning. Political leaders now weigh pykrete not against desperation but against practicality. They ask whether the project still offers decisive advantage. They ask whether resources should instead support proven methods. Some scientists urge continued experimentation. They argue that breakthroughs often arise from unconventional ideas. They warn that abandoning the project too early may forfeit long-term benefits. But most military planners focus on immediate victory. If escort carriers can already protect convoys, then the frozen vessel becomes an option, not a necessity. In Canada, the prototype continues to sit in the cold lake. Workers measure temperature changes. They inspect the surface for cracks. They note that the structure remains stable. They also know that the prototype is a world away from the massive construction proposed. Rumors circulate among staff. Some believe the project may continue. Some believe cancellation is near. Some simply wait for orders while the snow melts around the lake. Across Allied headquarters, the final recommendation begins to form. The frozen supercarrier is possible. The frozen supercarrier is innovative. The frozen supercarrier may be useful, but the frozen supercarrier is no longer required in a war turning in favor of the Allies. The momentum of events now presses toward a single outcome, a conclusion that will end one of the most extraordinary engineering proposals of the Second World War. The decision is close. Early summer 1943, London receives the last technical reports from Canada. The findings arrive in thick folders stacked across conference tables. Officers read every page carefully: heat loss projections, material estimates, refrigeration energy demands, reinforcement requirements for the steel frame. All evidence points in one direction. The concept works in theory, yet the scale defies wartime reality. The Admiralty meets again inside crowded rooms lit by steady lamps. Charts cover the walls, models of ships fill wooden shelves. Every discussion centers on one question: does the Atlantic still require a floating airfield made from frozen composite? By this point, Allied forces have closed nearly all remaining gaps in air coverage. Escort carriers travel with most convoys. Long-range bombers strike U-boats with growing success. Submarine losses climb. Convoy sinkings fall. The pressure that once drove Project Habakkuk now fades. Churchill reviews the reports. He appreciates bold ideas. He values scientific creativity. He admires the effort behind the project. Yet he also sees the growing strength of Allied forces. He sees the turning tide of the Battle of the Atlantic. He sees that resources are needed elsewhere. During this same period, the Canadian prototype reaches its last weeks. The ice grows soft. The structure begins to sag along the edges. Workers examine the surface. They take final measurements. They observe that the pykrete model still resists collapse even in warmer weather. It is a small but impressive testament to the material research. Then orders arrive. Project Habakkuk will not proceed to full construction. Funding ends. Staff return to other wartime duties. The frozen concept that once captured imagination now becomes a closed file stored deep within military archives. Months later, the prototype in Lake Patricia is allowed to melt naturally. The wooden framework settles into the water. The last fragments of the experiment sink quietly beneath the surface. For many, the project becomes a footnote. For others, it remains a remarkable example of wartime innovation, a vision too large for the moment that created it. Yet the idea leaves a legacy. It proves that unconventional thinking can influence strategic planning. It shows how scientific creativity can expand military possibilities. It reveals that even extreme concepts may shape future engineering research. Project Habakkuk never sailed, yet it stands as a reminder of the vast imagination unlocked by urgent need during the Second World War. One final question lingers. What might have happened if the Atlantic battle had continued to worsen, forcing the Allies to build a ship made from ice and wood pulp, on a scale the world had never seen?